Welcome again to everybody this morning. Just a couple quick comments. Remember that if you're a student and you need to have somebody know that you've been here, you can scan on your way out, not on the way in for this event. We are so grateful to Merck for helping support the variety of speakers that we've had that have made this possible. I keep getting just feedback after feedback about how amazing this lineup is, and I absolutely agree. This has been a lot of fun for me. Wanted to make a quick plug also for tomorrow. We're doing a dog expo out at the football practice field. We're raising money for Friends of Paws in Prison. It's a really important program. A few claps there, great. And so come out and check that out. And right now I'm going to get out of the way so my colleague, Dr. Mike Zuckery, can introduce our next speaker.
Good morning. I'm quite pleased to have been asked to introduce our next Krost speaker, Dr. Gregory Berns. Dr. Berns is the Distinguished Professor of Neuroeconomics at Emory University, as well as a member of the Psychology Department, where he leads the first team to train dogs to go into an MRI scanner to decode their thoughts and feelings. He received his PhD in biomedical engineering at the University of California, Davis in 1990, and his MD in medicine at the University of California, San Diego in 1994. He's the author of such books as Satisfaction, The Science of Finding True Fulfillment, Iconoclast, What Neuroscience Reveals About How to Think Differently, How Dogs Love Us, and What It's Like to Be a Dog, all of which have received enthusiastic critical acclaim. Dr. Berns' research is frequently the subject of popular media coverage in both print and on television, and he's also the co-founder of DogStar Technologies, a company using neuroscience to enhance the dog-human partnership. Dr. Berns notes that he currently lives in Atlanta with his wife and too many dogs. Please help me give a warm welcome to Dr. Berns.
All right. Well, it's great to be here, and I see it's kind of a varied audience. And so what I'm going to talk about today is what we familiarly call the Dog Project in Atlanta. And as you heard, this is a project that I started now 7 years ago. It was really just a side project. So before I did any of the dog work, I'd spent most of my career putting humans in MRI scanners so we could figure out what they're thinking, specifically how their reward systems work. And what I'm going to tell you about started with my own dog and now has become really the only thing that I do. So I just want to acknowledge our funders and the disclosure that I do own DogStar Technologies. So just quick outline of what I'm going to talk about. So I'm going to talk first about why we're MRIing dogs, so why use MRI in the first place, the philosophy, and how we do the training. So I'm going to show you some of our training videos so you have an idea, and maybe hopefully some of you will be interested in doing that if you have access to an MRI. A little bit about brain anatomy, and then I'll talk about the types of studies that we're currently doing and have done, and that breaks down into basic reward type tasks, studies of perception, and then the most difficult of all, which is having the dog do something in the scanner, and you'll see why that's actually quite difficult. And hopefully if I have time, because I understand that there's veterinarians and people who work in the health fields here, talk about some of the diseases that we're picking up. As you'll see, because this project has now gone on for 7 or 8 years, we are approaching really the end of the life of many of the dogs that started the project, and we've actually been picking up some of the diseases that older dogs get, and in some cases making a difference in their treatment. So that's kind of an unexpected side effect of the project. So why do we MRI dogs? Well, there's several reasons. Some of it is from just a basic science perspective. So if we kind of consider the dog-human relationship, so essentially the coevolution of dogs and humans, studying the dog brain gives us an insight not only into how dogs became dogs, we think, but also kind of an aspect of how humans became humans. And so as you'll see, all of our studies really are about the interaction of a dog and a human, because the humans are active participants in these studies, as you'll see. There are practical benefits in terms of training. One of the studies I'll tell you about has to do with the most efficient ways to communicate with dogs, specifically what is the sensory modality that's most efficient for them to learn in. And then finally, just trying to understand what makes the dogs so hypersocial, what makes them different than, say, a wolf or even a cat. So many of these studies are all very just basic, but now getting into the more applied aspects of the work. Okay, so my favorite philosopher, Gary Larson, how to recognize the moods of an Irish setter. I haven't seen an Irish setter since I was a kid, but you can replace this with a lab or a golden, and it works just as well. So this, to me, is the essence of the problem. We historically try to understand what's going on in a dog's head from their outward behavior because, of course, we don't have a choice. They don't speak to us, at least not in human language. So we have to make inferences about what their mood states are and why or why not they do things. And this is quite problematic because unless you're a dog, you might not necessarily be reading them correctly. I've certainly been fooled many times, and particularly with dogs that are rather stoic and not very demonstrative with what we perceive as emotions, it can be really difficult to know what they're thinking and what they're feeling. And I think oftentimes behavior can lead us astray as well, because sometimes when a dog doesn't do something, for example, we don't know why. Is it because they don't understand what we want them to do, or they do understand and they just don't want to? Very different. And so this is really the main thrust of my research, is using brain imaging to get around some of these constraints of outward behavior and go directly to the brain to see if we can understand and decode what dogs are thinking and feeling directly. There is also, of course, a dark side to dogs. We don't often talk about it in audiences like this, but it is worth pointing out that dogs do bite a lot of people worldwide and in the US. And so there is certainly a public health aspect to this work and trying to understand, for example, why some dogs are more aggressive and have stronger bite tendencies than others. So some of our work relates to that as well. Okay, so this is where we bring in the heavy equipment. So this is an MRI scanner being installed in our psychology building, and this is the tool that we use. So it looks kind of like a jet engine, probably weighs about as much. But it is exactly the same as a human MRI scanner. So the trick is, how do we teach dogs to go into that machine? So a little bit about our philosophy, and then I'll show you how we do that. So when I started this project, I established certain ethical principles that actually go above and beyond what's legally required by law in the United States. So all animal research is governed by the Animal Welfare Act. What we're doing is actually far beyond that. So first of all, we're not doing anything to hurt the animals. That means that we're not using any restraints, which means no physical restraints and no chemical restraints. So they're not sedated or anesthetized. All we're doing is trying to teach them how to go into this very weird machine that humans find unpleasant and trying to make it a game for the dogs, in essence. Because they don't know what an MRI scanner is, so they have no preconceptions about it. We use only positive reinforcement, and also critically, we only use community dogs, so we don't purchase laboratory beagles. These are just people volunteering for the project. We teach them how to teach their dogs how to go in the scanner. So there's a lot of challenges in doing this. The biggest one is you can't move. So if you've had an MRI, you go in the scanner and the tech says, okay, hold still. That's great if you don't mind very enclosed spaces and you're not claustrophobic, but of course many people are and they find it very unpleasant. So the challenge of no movement holds for humans, but particularly for dogs as well. It's a novel environment, so the dog hasn't seen it before, so we have to do a lot to get them familiar with it, so it's not novel. It's an enclosed space, so humans typically don't like enclosed spaces. It's rather coffin-like. That's not as much a problem for dogs. It's rather easy to teach them to go through tunnels, and that's part of our training. The one thing, though, that is a little disconcerting potentially for dogs is that it's elevated, so the patient table is about 3 feet off the floor, and so as you'll see, we teach them to walk up onto that table, which is a blind walk. but it's actually very similar to the types of things that dogs do in agility training. So that's all part of the training process. The kicker, though, is that an MRI is quite loud. It's about 95 decibels, sounds like a jackhammer. So we spend a lot of time getting the dogs used to that noise. We also teach them to wear ear protection, just like humans do. So that means either earmuffs or earplugs. All right, so this is how it started. So Callie is my dog. She has no particular skills other than this one very special trick. She was adopted from the Atlanta Humane Society probably back in 2010. And she was, I think, about a year and a half when we started this. The other initial dog is a border collie named Mackenzie. So I'm going to show you a little training video. It's about 5 minutes long, and I'll narrate as we go. Let's see if this starts. I think so. Yeah, great. Okay, so this is Mark Spivak. He's the dog trainer I partnered with and working with Callie. So what you see here, this is literally the first day that we started this. And he's using clicker training. And Callie has never seen this contraption before, and we're just trying to coax her into it. That is actually a mock-up of what we call the head coil. So that is what the dogs are going to have to go into. They're going to have to stick their head in there, and that will pick up the signals in the actual MRI scanner. I have to emphasize, when we started this at this stage, I had no idea whether it was going to work. I didn't know if the dogs would hold still.
Nice. Excellent.
Okay, here's Mackenzie. Now, Mackenzie was already pretty skilled in agility, and as you'll see, this turns out to be trivial for her.
Good girl. Lots. Yes. Is she too far out now?
Yeah, basically we're looking for the brain thing,
Yes.
the brain case to be in the center of it. Right there. That's good. You're not doing this.
Lots. Yes.
So we played around with this probably for about half an hour, and I still didn't know if this was going to work, and then Mackenzie did this. Very typical border collie stare, right? So it was at that point, it's like, okay, yeah, we're going to be able to do this. This is possible now. Okay, so that's how it started. As good as that was, still way too much movement. What we have to get the dogs down to is about no more than 1 millimeter or 2 of motion. So the first thing we did was introduce a little chin rest to give them something to put their head on. And that helps a bit. These are all my home movies now.
Yes.
There's Mackenzie trying it. Now, you notice she's also actually inside a big tube. So that is what we call the MRI Simulator. It is just a big tube. Okay, so this is after probably a couple of weeks of messing around with this. That noise you hear, that is a recording of the scanner noise, which I would just play kind of ambiently at low volume, and just to get her used to it. And the idea is, when they hear that sound, they know it's playtime, and this is how we play.
Perfect.
Plus, she gets treats too.
That's what we want.
Okay, so this is after a month or two. This is at the real scanner. This is the most expensive training session ever, because I had to pay for the scanner time, which is $500 an hour. So you also notice we introduced pet steps, and so I had been working with her at home to walk up the steps. So the idea is the dogs walk into the scanner of their own volition. That way, they know the way in, and they also know the way out. So they can also leave when they want.
On the second trial, Callie went right up the stairs.
Okay, and this is probably after about 2 or 3 months of training. You notice we also modified the chin rest, so it now conforms to her muzzle, custom fit for her, which gives her feedback both kind of in all the planes necessary, up and down, side to side, and backward, forward. Also notice she's also wearing little earmuffs. And I've introduced hand signals at this point. Okay, and so that's how you train a dog for MRI. It looks easy, right? In hindsight, it actually is not that hard. So when I go around telling people about this, especially actually veterinarians, when we started this, there was a lot of skepticism of whether the dogs would hold still. But really, when you break it down like this, and originally it was all trial and error, but now, 7, 8 years later, we've trained and scanned 100 dogs. It's really quite straightforward. And a lot of it has to do with selection, subject selection. So we have a tryout process now. This is more contemporary. This I filmed last year just to show you a different dog and a new scanner. John, can we play this video? This is Tug, Portuguese water dog. Okay, and let's play this one too. So this is with the scanner running. Okay, so it works for big dogs too. So we've scanned dogs anywhere from 18 pounds up to over 100 pounds. And that has to do with the coils that we use that allow all shapes and sizes now. So just a few cheesecake shots. There's Callie. You'll notice in a lot of these pictures, the dogs have vet wrap on their head. That's to hold either the earplugs or earmuffs in place so they don't fall off or so they don't shake them off. This is what it looks like from the other end. So the dog's in the coil, and then we interact with the dog from the other side of the scanner. That's the dog's owner. And then hopefully we end up with happy dogs and happy humans. So that dog's name is Katie. She appears in a lot of these videos you'll see. And then so what happened after that, once we were convinced that this would work, then of course we put out word of mouth that we're looking for owners to volunteer this new project and train their dogs to go in the MRI. And we didn't know what we would find, but we started with initially these 6 dogs, which we called the A-Team. Then after the A-Team, there was Bravo Company. And then after that, it kind of just took off. So we've now gone through 8 training cohorts. So we typically do a training cohort. Now we're down to about once a year because we have so many dogs trained already. We don't need more, but we'll probably start a new one. But I hope you get a sense that this is very much a citizen science project with the community participating and just a very wide range of dogs. Okay, so that's how we do it. So now I'll tell you a little bit about some of the things that we found and kind of how we got there. So first, a little bit about brain anatomy. So just for comparison, I put these up. This is not to scale. A typical dog's brain is about the size of a lemon, so it fits in your hand. So this is scaled up. But I just want to point out that there's a lot of similarity in structure, and you can identify them. So you can identify things like the brainstem and the spinal cord here, brainstem, spinal cord, cerebellum, cerebellum. This is the corpus callosum here, connects the left and right hemispheres. Same here. The main difference that seems to be the most obvious is in what we call the cortex. So humans obviously have a much larger cortex than the dogs. It's also more folded, meaning that you see a lot more of these squiggles here than the dog. And then kind of more granularly, the human frontal lobe starts about here. So this is all human frontal lobe. The dog frontal lobe starts probably about here. So relatively much less frontal lobe for the dog. The one thing, though, that is relatively larger is right here. That's their olfactory bulb. You can't see it in the human image, but the dog's olfactory system is obviously more important to them than ours is to us. Just another view. This is kind of slicing from top down. One of the structures that I'm going to talk a fair bit about is where the arrows are pointed. This is a structure called the caudate nucleus. It's one of the parts of the brain that has the densest concentration of dopamine receptors, and because of that, we know that it's critically involved in things like reward, motivation, and learning. And so it's easy to identify the same corresponding structure in the dog. It's right there. I say it looks like a footprint from a deer, kind of a little chevron kind of thing there. So initially, all of our studies are looking at that structure because we already have an idea of how that functions in other animals. And so when we started, it was just proof of concept. Okay, so that's what I'm going to tell you about right now, is the reward studies. So those hand signals that you saw in the video is where we started with this. We actually did that for a reason, well, two reasons. One, we weren't sure the dogs could hear us in the scanner, so we introduced hand signals. But the other reason is just to do something very basic. It's essentially just Pavlovian or classical conditioning. So what we did was we taught the dogs that when you see this hand signal, hold still, and you'll get a treat. And as a control signal, we just hold the hands up like this, which just controls for the fact that we're holding hands up, but nothing happens after that. So that's essentially the comparison condition, and kind of looks like that. So the whole game with fMRI is you compare relative brain activity. It's actually blood flow that we're looking at from one condition to another. And so what we're looking for is a difference between this condition and this condition. Now I want to emphasize that what we're looking at is the response to the hand signals, not the response to food, because when the dogs eat the food, their head is moving, obviously, so we don't get any data when they're eating. So all of the experiments that we have to do are set up to create a state of anticipation, in which case then we can measure activity because the dog is holding still, and actually anticipation is a very powerful driver of the reward system. So when we did that, initially with just Callie and Mackenzie, in fact, we saw activity in that structure. So you'll see some of these images where you see these kind of colored maps. That's just a shorthand way of identifying the locations in the brain where there were statistically significant increases in activity, okay? And usually the intensity encodes or codes for the significance itself. So more intense, more statistically significant. And then we can plot the time course of that activity. So this is each scan, that's roughly about 1.5 seconds between each scan. And then the solid line is the response to this hand signal, and the dashed line is the control signal. And so you can see how that reward hand signal causes a rise in activity, which is exactly what we predicted based on 100 years of research on that structure. So that's great. As my colleague said, that's fascinating. You just proved that dogs like hot dogs. Yes, that's true. So one of the things that we did immediately after that, it was after we expanded the cohort, then we confirmed that it replicated in a larger number of dogs. So this, again, is one of those colored maps where the redder it is, the more significant the increase to that hand signal. And the reason I show this is it could have been the case that we just got lucky, that maybe some other random part of the brain would increase in activity, but it's actually quite specific. So it's actually only that area, which is incredibly important because it means that, yes, we are picking up the signal that we think it is, and it's not just we just kind of got a random splotch in that part of the brain. It really is specific. So that led us on to to keep going. So one of the things that we did, and now I'm kind of jumping out of the actual temporal order that we did, is use that type of study. We partnered with Canine Companions for Independence, CCI, to see if we could modify that and predict which dogs would be good service dogs. So I see many service dogs here, maybe service dogs in training. So as you know, it's very time-consuming and costly to train these dogs, and depending on which organization you're working with, they might have a success rate of anywhere from 35 to 50%. So there's a high washout rate. So what we did with CCI was we taught their trainers how to do the MRI training. We built a simulator on their campus in Santa Rosa, California, and over the course of 2 years, trained and scanned 50 of their dogs that were entering advanced training. So these are dogs that are between 16 and 18 months of age. And we did exactly the task that I just showed you with these hand signals, with one little twist. We had the trainer, the dog's trainers give the hand signal, and then either me or my partner Mark would come in and give the signals as a stranger, okay? So we figured that this would be a good test for potential service dogs, because what it's doing is it tests several things. It tests how the dog's brain responds to incentives. So, you know, these hand signals are incentives or motivation signals. So how willing is their brain to learn? But also importantly, how do they respond to a stranger giving those signals? So this is incredibly important for a service dog, because they have to transfer their learning to another person. But on the other hand, if they're too willing to do that, then they might be too distractible, right? So they could be walking down the street, and then any person might grab their attention. So we hypothesized that there was actually a sweet spot to this. These are just some of the mug shots of the dogs. This is not even all of them. This is just the ones I could fit on one slide. We did this scanning at UC Berkeley, so we would fly out there every 3 months to scan a dozen dogs on a weekend. Okay, so again, kind of where we're looking for these things. So we're looking in the caudate nucleus as the center of reward and motivation and learning. We're looking in another area called the amygdala, which is associated with arousal, both good and bad types of arousal. And then also an area kind of towards the back of the brain that we believed is involved in face processing. And I'll come back to that in a little bit. So what we found, actually, and sorry, this is a little bit of a technical slide. This is a type of graph that we use to talk about diagnostic tests. And it shows how good we were at predicting which dogs would be good service dogs. So we scanned the dogs, and then we just had to wait to see if they actually graduated and were placed with a person. And that constituted either success or failure. So this type of plot, which is called a receiver operating curve, plots the true positive rate, so the chance of correctly predicting a service dog, against the false positive rate, so incorrectly predicting the dogs. So a perfect test, perfect diagnostic test would have a curve that kind of went like that, because that would mean you picked up 100% of the true positives and got no false positives. The diagonal is basically 50-50 chance. And so what you see is, in actuality, we're kind of in between there. So if you run the numbers, we actually were able to predict about 80% of the dogs. We were about 80% accurate, which was actually slightly higher than the trainers themselves based on the internal metrics that they use. And what's neat about this is that all the dogs did the task, and yet we were able to look in their brain. There's what we call covert activity going on during the task that seemed to indicate something about their thought processes that discriminated good dogs from bad dogs, or good service dogs from not good service dogs. And one of the key structures turned out to be the amygdala. And so what we think we were picking up is, even though the dogs were doing the task, some of the dogs were a little more aroused by it. Some good, some bad. So some dogs probably were a bit nervous, even though they were still doing it. Other dogs were just like, yeah, man, let's do this. New person, I want to play with them. That's also a form of arousal. And they all did it, but their brains were showing that there was more going on there. And so this kind of goes back to that Gary Larson slide, is it looked like they were all doing it, but they were not all thinking and feeling the same thing. Okay, so that leads to a variant of one of the experiments. So kind of for a long time, I wanted to know, is it all about the food? And so we designed an experiment to test this. This is what we call the praise versus food experiment. So this is Katie in our simulator. This is a very simple experiment. You're going to see there are three objects, a hairbrush, a pink car, and a blue horse. The hairbrush is just a control thing that we hold up. Nothing happens after it. The reason we're doing this is because we're after social reward. We're trying to separate social from food reward, and we can't have the human there giving hand signals because that itself is a form of social reward. So the human's out of sight, and then we hold up these objects from below. So can we play the video? Okay. Okay, so there's the hairbrush. Nothing follows the hairbrush. Next up will be the pink car. She's really good at this. Sometimes it's hard to tell that the video is even playing.
Yay, good girl.
Okay, so that's her social reward. You can't tell what she's thinking. Okay, and then next up will be the blue horse, and that's going to be followed by what we call the treat kebab. So it's got a piece of hot dog skewered on a stick. Okay, so that's what we do in the scanner, and again, it's about the state of anticipation, so we simply compare the response to that pink car versus the blue horse while they're waiting for either the praise or the food. And then we go in and we look at the response in that caudate nucleus, because that we're using as a gauge of how much they're anticipating that particular type of reward. And they've all been trained on this outside the scanner. So before I show you the results, we also did, this is one of the few behavioral tests that we did. We give them a choice test, what we call the Pepsi challenge. So the dog is behind that door, and they have this kind of V maze. And there's a food bowl here, so there's a treat in the food bowl. They've been familiarized with this. So they have to make a choice. Do they go to their owner and get praise, or do they go for the food? And we do this 20 times for each dog. Okay, can we play that video? This dog's name is Ohana.
Okay, praise.
All right, great. Happy dog, happy owner. But let's do it again. Let's play this video. Okay, so that's pretty typical. Although what turned out to be interesting, so we flip-flopped the sides, alternate trials, so because dogs, as many of you know, develop side biases. What was most interesting about this, so you can tabulate the percent of times they go to their owner versus the food, but actually what turns out to be more interesting is the sequence that they do. So some dogs are what I call samplers. They just kind of go back and forth between dog and between food and owner to whatever kind of they titrate their comfort level. And then other dogs stick with one for many, many trials and then switch, and then they stick with that. And those are actually very different types of sampling patterns. And what turned out is that, before I get to that, so how it turned out is that most of the dogs, approximately 75–80% of them, their caudate nucleus showed an equal response or greater response to the praise as the food. So kind of just at first pass, based on the brain response, we're fairly confident that the dogs value their praise as much as food. And for some dogs, even praise is even more valuable. And then there were a couple dogs where it was flipped around. And what's interesting is that it corresponded to the patterns that they exhibited on this behavioral task. And so we're beginning to show the links between the brain activity, which is fundamentally a passive response because they're not doing anything, with activity patterns and actually personality patterns as well outside the scanner. One of the things I think is interesting and perhaps the most relevant from a training perspective, which we only recently did, is ask the question, what modality is best for the dog? So in the experiments I've shown you, we've used visual stimuli, either hand signals or objects, but that may not be the best way to communicate with a dog. And certainly from our human perspective, we tend to use language, and we don't yet know kind of the extent that the dogs respond to language as such. So we did a very similar experiment. So instead of, we had a condition where we used objects, which you see on the left in terms of visual stimuli. Again, same idea. We teach the dogs, we hold up an object, and one is either followed by a treat and the other one isn't. And we just measure that in the scanner. Unlike the previous experiments, though, the training is actually done in the scanner. So we're actually trying to measure learning itself. So we're trying to measure how that activity in the caudate goes from 0 to something non-zero, and how fast does it do that? How many trials does it take? And so we do that with visual stimuli. We do that with olfactory stimuli. So you see there's a little pipe here. That's attached to something called an olfactometer, which is just a pump connected to two odorants. In this case, we used isomyl acetate and hexanol. So those are just two arbitrary chemicals that they wouldn't have experienced. And one is followed by a treat and the other one isn't. And then we also use verbal stimuli. So here you can kind of see it. You can't see it too well. There's a word up there. So the human just speaks that word. And it's a gibberish word. I think it's from Jabberwocky, the poem Jabberwocky. And so one of those words is followed by a treat and the other one isn't. And so then we use the caudate nucleus to measure the rate of change. Basically, how fast does it pick up those associations? And so we go in, and these are the areas that we looked at, mainly the caudate and the amygdala, as well as an area in their temporal lobe. And this is what we found. So here are the three areas. The one I want you to focus on, although they all show the same pattern. But if you look at the caudate, that's the area that we think is most significant for learning. The blue represents the visual stimuli, and red, the olfactory stimuli, and green, the verbal. For all of all these regions, the visual and the olfactory stimuli are the most efficient at learning. The dogs learn the fastest from that. And this is important because it means that dogs are probably visual learners, better than verbal learners. And we already know that they're very good at picking up odorants. There could be several explanations for why verbal wasn't as efficient, one being that the scanner is quite loud and they have to discriminate over that. But it could also represent the fact that dogs are just not wired like we are for language. They can learn some things, but we think that they're learning it in a way very different than we do. Okay, so moving on real quick. So some of the perception studies. Early on, we studied odorants. We studied biological odorants. So we would present scents from a familiar human, unfamiliar human, a familiar dog, and an unfamiliar dog, and their own scent. And again, what we found, so again, these plots, so if we look at the response to all the smells, we see activity in this part of the brain. That's their olfactory bulb and olfactory cortex. Not surprising. What is interesting, and it's a little bit hard to see here, is again, when we go back to the caudate, it's most active to familiar smells, and specifically the smell of the familiar human, much more so than actually a familiar dog, which is a little bit of a surprise to us because we thought that another dog in the house would be the most salient odor to the dog, but it turned out the scent of the human was, which is interesting. Moving on, we've also studied response to faces. So until recently, in neuroscience, it's been well known that there's a part of the primate brain that responds to faces. It's called the fusiform face area. This was one of the first experiments that we did where we literally just copied a human experiment. So the way this experiment goes is we show pictures to the dogs. So you can see this is Callie looking at a picture of a dog in the scanner. And the types of pictures we show look like this. We show pictures of humans, of dogs, of everyday objects, natural scenes, and then just scrambled versions of those. So in the human literature, the face area is typically defined by faces relative to objects. So it's a part of the brain that responds only to faces in that sense. And so we did exactly the same thing. First, we identified a part of the brain that responds to all classes of stimuli. So here, each dot is actually a dog, not statistical significance, but they all cluster in a particular area towards the top of the brain, which is called V1 because it's primary visual cortex. And in fact, all the types of stimuli elicit activity there. What's more interesting, though, is an area which we call DFA, for dog face area, which has a response only to faces relative to these objects. And so it follows the same pattern as we see in humans and other primates, and that area is located more to the side in what we call the temporal lobe. So it's an analogous region. It's in roughly the same area, we think, as the human and the primate version. So dogs, we think, come wired for faces, too. Okay, so one of the big questions, so another Gary Larson cartoon, what we call the ginger effect. What exactly do dogs get from human language? It's really difficult to say because we talk constantly, frequently without saying much. And honestly, it's amazing to me that dogs are able to get anything out of that kind of stream of gibberish. So we undertook a study. This was incredibly difficult. We studied something called words and pseudowords. And to do this, we had to first teach the dogs the names of some new objects. So we gave them arbitrary names. And this is based on the famous dog Chaser, who knew 1,000 objects. So we basically just did the same thing with a very simple goal of teaching the dogs the names of 2 new toys. And so in the scanner, what would happen is the owner would be there speaking the particular word, and then they'd have a bucket of toys, some of which corresponded to their toy, but most of which were just random new toys as control. Here are our participants. Surprisingly, it took 6 months to train most of these dogs the names of just 2 random objects. I can talk afterwards of why I think it was so hard. Part of it, I think, is that they're all adult dogs. And to date, most of the dogs that have been documented to have large vocabularies were trained from almost from birth. So it may be that there are critical periods for this in dogs. And what we found, interestingly, we also had a control conditions for the trained words, which we called pseudowords. And again, these are just gibberish words that the dogs hadn't heard before. What we found is actually that these gibberish words elicited more activity in a part of their temporal lobe, here, here, and here, which we think corresponds to their auditory cortex and kind of a rudimentary language processing area. Interestingly, this pattern on this type of experiment is opposite to what we see in humans. So when you do this with humans, you get more activity to words that you know as opposed to gibberish. Probably because when you hear a word that you know, it triggers all sorts of downstream processing. Whereas if you hear gibberish, it's like, I don't know what that is, there's nothing more to do with it. We think, and this is why I think dogs process language in a way that's quite different than us. The fact that it's opposite in dogs, to me, suggests that when a dog hears something new, their kind of motivation is to figure it out, because that's kind of the norm around the humans. When they hear a new word, usually it's associated with something the human wants them to do. So a lot of these dogs, because they're so well trained, then kind of go into that, hey, what does that mean? They want me to do something mode, and that triggers more processing. Kind of going even deeper, we can also perform a fairly sophisticated computer algorithm analysis, machine learning, or type of artificial intelligence analysis that tells us what parts of the brain might be representing the difference between the words that they know. And that identifies kind of these structures here in the temporal lobe. When we talk about kind of words representing things, now we're getting into the realm of semantics. And this is quite deep, because This is the definition of language, or part of it. A word represents something, and that's abstract knowledge. For comparison, you do the same thing in humans. This represents kind of an aggregate of all the studies that have been done. You see very similar patterns in human brains of where these types of semantic or knowledge networks are. So I just want to point out that similarity. Okay, so moving on just real quick, the one active task that we did, quite difficult, is something called the go, no go task. It's challenging because if you ask a dog to do something, they're going to move. So we designed a task where the task was not to move, but with an added condition. And first we taught the dogs a nose poke. So you see there's a little target in front of Callie. I have a dog whistle in my mouth, so when I blow the dog whistle, she's supposed to just nose poke that target. That's pretty easy to teach. What's hard, though, is after they learn that, we introduced a new hand signal that looks like this. That means don't poke the target even when you hear the whistle. Okay, so we can play this video. Okay, so this is just the standard, hold still, you get a treat. Okay, okay, that's a false alarm. She moved, she wasn't supposed to. This is what it's supposed to look like. And then just to show you that she knows the whistle means go.
Good.
Okay, so that's it. That also took 6 months to train. It's much easier to train dogs to do things than not to do things, especially after they've learned to do them in the first place. So when we do this, the key comparison is this. It's the comparison of this versus this, because in both cases, the dog is not moving. The difference is, in this condition, they're putting on the brakes. And so this is what we call self-control or impulse control. And when we do that, we find an area in their frontal lobe. Not big frontal lobe, not a big area of activation, but this is the area we think that's responsible for impulse control or self-control of the dog. And it turns out, when you do this in humans, you get exactly the same pattern. Same part of the frontal lobe in humans does this. So we think this is the same thing. And what's even more interesting is that the dogs who had more activity there had fewer false alarms as well. So there's a correspondence then. The more activity that the dog is able to elicit, the better that they do. Okay, so almost done. I do want to touch on kind of this issue of diseases. As I said, we've been doing this a long time, and the dogs are getting old, which is sad. This dog, Libby, she's a mix. She was probably about 6 when she started it. This is what she looks like now. I know, it is sad. She's a lumpy dog. You can see she's got lipomas all over her body, and this is what her body looks like. So I've been showing you brains, but we quickly realized it's like, well, hey, the dog's in the scanner. All we have to do is move our field of view down to their abdomen, and we can scan their body too, basically looking for tumors. And you can see there's a big lipoma right there. That's a benign tumor. She's just a lumpy dog. Not everything, though, is benign, unfortunately. So we have this dog, Kirby. Kirby has epilepsy, rather poorly controlled, even on 3 medications. His owner joined the project specifically, I think, because she wanted an MRI of Kirby. And we said, fine, if he can go through the training. And he did. He did really well. And so we did the first scan, and this is what we saw in his brain. These are the ventricles. They're enlarged, not to the point of being called hydrocephalus, but they are definitely enlarged. And this is actually not uncommon in epilepsy, both in dogs and humans. We don't know if repeated seizures kind of cause that kind of damage in the expansion of the ventricles, or whether it predisposes to that. But it points out that we can do clinical scans in clinical populations. And I should say, these structural scans here only take 30 seconds to do. Which leads us to this dog, Stella Bouvier, had been participating for a long time as well, and had just done one of our studies, and as she was leaving, the owner just casually said, you know, Stella had a nosebleed last week. I like, okay, well, let's put her back in the scanner. We'll do a quick structural scan. Again, it only takes 30 seconds. We don't need anesthesia or anything. And unfortunately, this is what we found. The right side of her nose was completely socked in. But because we picked it up, we made the diagnosis, we were able to refer her to University of Georgia Veterinary Hospital, and they did radiation. And so we were able to follow Stella repeatedly. Because she could do the MRI, and because it would only take, I mean, it really only took like 5 minutes. It took longer just to kind of get everything set up. Once she would just hop in, like you saw the dog, and we do the scan, 30 seconds, and we're done. We were doing this every couple weeks and following how the tumor regressed following the radiation, which nobody does because you can't do repeated MRIs like that on dogs. It's too costly and it requires anesthesia. So I'm telling you, it doesn't have to be that way. Then this is Jack. Jack, very similar to Stella. The owner called me one day. I said Jack had a seizure. He was 12 at the time. He had been in the project since he was about 6. And we can track the development. He developed a brain tumor. So this is a normal scan in 2014. In 2016, in March, you can see there's a bit of a hyperintensity here, which becomes more obvious in this one in August 2016, which is when he had his first seizure. This I didn't notice at the time. It was only kind of in hindsight that I went back and looked for it and kind of amplified the contrast. But it's important because things like this, it's not really well described the natural course of brain tumors in dogs because typically you only become aware of them when they have a seizure and it's too late to do anything about it. And I mean, Jack was really too old to do much anyway, but it also points out that the tumor was there for at least 5 or 6 months, probably longer, and he was asymptomatic. And perhaps in a younger dog, if we pick that up, we might, the owner might have undertaken treatment. Again, it's kind of a new area in veterinary medicine because it's not normally done. So that's it. Just to recap, I told you about why we're MRIing dogs, the philosophy and training we've had, and the types of studies, including reward, perception, and active tasks, as well as some of the diseases that we're picking up. So, thank you. Up for